Hello students, in this lecture we will discuss few numerical problems related to entropy, available energy and irreversibility. 1 kilogram of water at 273 Kelvin is brought into contact with a heat reservoir at 373 Kelvin. When the water has reached 373 Kelvin, find the entropy change of the water, of the heat reservoir and of the universe. If water is heated from 273 to 373 Kelvin by first bringing it in contact with a reservoir at 323 Kelvin and then with a reservoir at 373 Kelvin, what will the entropy change of universe be? Now, here we are having 1 kilogram of water at 273 Kelvin as a system. Now this system is brought into contact with a heat reservoir which is maintained at 373 Kelvin. In the second part of this question, the same system, that is 1 kilogram of water 273 Kelvin, that is first brought into contact with a reservoir at 323 Kelvin, and then it is brought into contact with another heat reservoir which is maintained at 373 Kelvin. So what the entropy change of the universe is going to be in this case? Now we take up the case A1, A first. So water is being heated through a finite temperature difference. The entropy of water would increase and that of reservoir would decrease, so that the net entropy change of the water, that is system, and the reservoir together would be a positive quantity. Water is being heated irreversibly, but as we have seen in the theory, that to find the entropy change of a substance, we assume a reversible path between the end states which are at equilibrium, because only then and then we can find out the magnitude of entropy change. So entropy change of water is equal to integration of del Q upon T. Del Q is equal to mc dt, where m is the mass of water, c is the specific heat of water. So this entropy change of water comes out to be 1.305 kilojoule per Kelvin. The reservoir temperature remains constant irrespective of the amount of heat withdrawn from it. Now, amount of heat absorbed by the system from the reservoir, that is given by mass into specific heat into temperature difference, that is 100 degrees. So that comes out to be 418.7 kilojoule. Now the entropy change of the reservoir. So 418.7 is the amount of heat given out or rejected by the reservoir, means given to the system, that is 1 kilogram of water. So because it is the heat rejected by the reservoir, so it will come with negative sign. So minus 418.7 upon 373, which is the absolute temperature, and the entropy change of the reservoir comes out to be minus 1.122 kilojoule per Kelvin. So the entropy change of the universe, which is the summation of the entropy change of system and the entropy change of the reservoir, it comes out to be 0.183 kilojoule per Kelvin. Now in the case B, in the second part of this question, water is being heated in two stages from 273 Kelvin to 323 Kelvin by bringing it in contact with a reservoir at 323 Kelvin, and then from 323 Kelvin to 373 Kelvin by bringing it in contact of a second reservoir at 373 Kelvin. So the entropy change of water has been split up in two parts and it will be added then. So in the first part, we are having the entropy change when the temperature is raised from 273 Kelvin to 323 Kelvin, and then in second part we are having the entropy change when the temperature is rising from 323 Kelvin to 373 Kelvin. So m is the mass of the water, c is the specific heat of water. So as done in the earlier part, similarly we get the value of entropy change of water as 1.305 kilojoule per Kelvin. Now the entropy change of the reservoir first means that is having the temperature of 323 Kelvin. So what is the amount of heat rejected by the reservoir that you have put in numerator? So that is minus 1 into 4.187 into the temperature difference divided by 323, which is the absolute temperature of the reservoir first. So the entropy change of the reservoir first one comes out to be minus 0.647 kilojoule per Kelvin. Now the entropy change of the reservoir second. So that is minus 1 into 4.187 into the temperature difference, that is 373 minus 323, divided by the absolute temperature of the reservoir, that is 373. So that comes out to be minus 0.56 kilojoule per Kelvin. Now the entropy change of the universe in this case will be the summation of the entropy change of the water and the entropy change of the both of the reservoirs. So that comes out to be 0.098 kilojoule per Kelvin. So we have seen that entropy change reduces if we are having or carrying out the process of heat transfer into number of stages. So the entropy change of the universe would be less and less if water is heated in more and more stages by bringing the water in contact successively with more and more heat reservoirs, each succeeding reservoir being at a higher temperature than the preceding one. When water is heated in infinite steps by bringing it in contact with an infinite number of reservoirs in succession, so that at any instant the temperature difference between the water and the reservoir in contact is infinitesimally small, then the net entropy change would be zero and the water would be reversibly heated. 1 kilogram of ice at minus 5 degrees Celsius is exposed to the atmosphere, which is at 20 degrees Celsius. The ice melts and comes into thermal equilibrium with the atmosphere. Determine the entropy increase of the universe. What is the minimum amount of work necessary to convert the water back into ice at minus 5 degrees Celsius? Cp of ice is 2.093 kilojoule per kg per Kelvin and the latent heat of fusion of ice is 333.3 kilojoule per kg. Now 1 kilogram of ice at minus 5 degrees Celsius is the system, and the atmosphere maintained at 20 degrees Celsius is a thermal energy reservoir, which means that its temperature will not change whatever may be the amount of energy interaction. The amount of heat absorbed by the ice is equal to the amount of heat given out or lost by the atmosphere. Now, the amount of heat absorbed by ice is equal to the heat absorbed when the substance is in solid phase plus the latent heat of fusion of ice plus the heat absorbed when substance is in liquid phase. Now heat absorbed in solid phase is equal to 1 into 2.093 into 5. 5 is basically the temperature difference, means minus 5 degrees Celsius of ice to 0 degrees Celsius ice. Now the latent heat of fusion is equal to 1 into 333.3. The heat absorbed in liquid phase is 1 into 4.187 into 20. Means when water at 0 degrees Celsius is converted to water at 20 degrees Celsius. So that basically accumulates to 427.5 kilojoule. Now the entropy change of the atmosphere. As I told you, the amount of heat absorbed by ice is equal to the amount of heat given out or lost by the atmosphere. So the amount of energy lost by the atmosphere is equal to 427.5. We have put negative sign because it is the amount of heat lost by the atmosphere. The atmospheric temperature is 20 degrees Celsius, so T has been put 293 Kelvin. So the entropy change of atmosphere is equal to minus 1.46 kilojoule per Kelvin. So the entropy change of the system, that is ice, as it gets heated from minus 5 degrees Celsius to 0 degrees Celsius, it will be del Q upon T, and del Q will be mCpT because we assume that heat transfer is taking place at constant pressure. So mcp dt upon T is integrated from 268 to 273 Kelvin, that is minus 5 degrees Celsius to 0 degrees Celsius. So that gives us 1 into 2.093 into natural log of 273 upon 268, and that basically gives us the value 0.0389 kilojoule per Kelvin. Now the entropy change of the system as ice melts at 0 degrees Celsius to become water at 0 degrees Celsius, that will be the latent heat of fusion of ice divided by the absolute temperature of the ice during fusion, that is 273. So that is basically 333.3 upon 273. That gives us the value of entropy as 1.22 kilojoule per Kelvin. Now the entropy change of water as it gets heated from 0 degrees Celsius to 20 degrees Celsius. Now the entropy change of the system when the temperature of water is raised from 0 degrees Celsius to 20 degrees Celsius can be obtained by integrating del Q upon T with the limit of 0 degrees Celsius and 20 degrees Celsius. Now del Q is equal to mcp dt, because it can be assumed that the heating of water takes place at constant pressure, and at constant pressure del Q will be equal to mcp dt. So when mcp dt upon T is integrated, the expression becomes mcp ln of T2 upon T1. So limits have been put as T1 is equal to 273 Kelvin and T2 is equal to 293 Kelvin. So the result comes out to be 0.296 kilojoule per Kelvin. Now the total entropy change of ice as it melts into water is equal to the entropy change for the first process plus entropy change for the second process plus entropy change for the third process. The first process was when the ice was heated from minus 5 degrees Celsius to 0 degrees Celsius. The second process was the fusion of ice into water, and the third process was the temperature rise of water from 0 degrees Celsius to 20 degrees Celsius. So all these three entropy have been added, and the results comes out to be 1.5549 kilojoule per Kelvin. Now the entropy increase of the universe is equal to the entropy change of the system, that is that of ice, and the entropy change of the atmosphere. Now to convert 1 kilogram of water at 0 degrees Celsius to ice at minus 5 degrees Celsius, as a part B of this question, let me tell you that 427.5 kilojoule of heat have to be removed from the ice, and the system has to be brought from state 4 to state 1. Now a refrigerator cycle as shown in the figure is assumed to accomplish this. The figure is shown on the next slide. Now this is the graph that is showing that how the entropy change is taking place in three processes that we have discussed. The entropy change of the system would be same S4 minus S1, with the only difference that its sign will be negative because heat is removed from the system. So the entropy change of the working fluid in the refrigerator would be 0 since it is operating in a cycle, and the entropy change of the system will be S1 minus S4. Now 1 kilogram of water at 20 degrees Celsius, which has to be converted into ice at minus 5 degrees Celsius, is our system. So for this we will have to extract 427.5 kilojoule of heat from this substance, that is 1 kilogram of water at 20 degrees Celsius. And for this we will have to employ a refrigeration cycle, and we will have to do work on the system means input of work is there. So Q plus W will be the amount of heat rejected to the atmosphere, which is maintained at 293 Kelvin. So the entropy change associated with the atmosphere, which is a thermal energy reservoir, is equal to Q plus W upon T. Now the entropy change of the universe will be the summation of entropy change of the system plus entropy change of the refrigerator plus entropy change of the atmosphere. So that becomes S1 minus S4 plus Q plus W upon T. So by the principle of increase of entropy, the entropy change of universe, or you can say isolated system, has to be a positive. So S1 minus S4 plus Q plus W upon T is greater than equal to 0. So that gives us the expression Q plus W upon T is greater than equal to S4 minus S1. W is greater than equal to T into S4 minus S1 minus Q. Now this expression says that work will be minimum if the equality sign is there. So the minimum work is equal to T into S4 minus S1 minus Q. The value of Q is equal to 427.5 kilojoule. T is equal to 293 Kelvin. So the value of S4 minus S1 is equal to 1.5549 kilojoule per Kelvin. And the amount of minimum work after putting all the values comes out to be 28.5 kilojoule. Two identical bodies of constant heat capacity are at same initial temperature Ti. A refrigerator operates between these two bodies until one body is cooled down to temperature T2. If the body remains at constant pressure and undergo no change of phase, show that minimum amount of work needed to do is Cp into Ti square upon T2 plus T2 minus 2Ti. Now, as shown in the diagram, body A is having initial temperature of Ti. Q amount of heat is being withdrawn from it, and W amount of work is being done on the system. And Q plus W is the amount of heat rejected to the body B, which is initially at temperature Ti. So basically, to execute this, refrigerator has been employed. Now both the finite bodies A and B are initially at the same temperature Ti. Body A is to be cooled to temperature T2 by operating the refrigerator, as I have told you just now. Let T2 dash be the final temperature of body B. So you can see here from the diagram that body A, which was having initial temperature Ti, its temperature dropped to temperature T2 because heat is being withdrawn from it. Whereas in the case of body B, which was having initially temperature of Ti, its temperature rises to T2 dash. Now heat removed from body A to cool it from Ti to T2 is equal to Q, which is equal to Cp into Ti minus T2, where Cp is the constant pressure heat capacity of the identical bodies A and B. Now heat discharge to body B is equal to Q plus W, and that is equal to Cp into T2 dash minus Ti. So work input will be equal to the heat discharged to the body B minus heat absorbed from the body A. So that is equal to Cp into T2 dash minus Ti minus Cp into Ti minus T2. So that gives us the value Cp into T2 dash plus T2 minus 2Ti. Now the entropy change of body A will be the integration of the term Cp dt upon T, where this expression is integrated from the lower limit of Ti to T2. So Cp into natural log of T2 upon Ti is the final expression for the entropy change of body A. Now the entropy change of the body V can also be obtained similarly, and we get the expression Cp into natural log of T2 dash upon Ti. Entropy change of the refrigerant will be 0 because it is executing a cycle. So the entropy change of the universe will be equal to the summation of entropy change of the body A and the entropy change of the body B. Now the entropy change of the universe, which is equal to Cp into ln of T2 upon Ti plus Cp into ln of T2 dash upon Ti. Now by the entropy principle we can say the entropy change of the universe has to be positive. So Cp ln T2 upon Ti plus Cp ln T2 dash upon Ti is greater than or equal to 0. This gives us Cp into ln T2 into T2 dash I upon Ti square is greater than or equal to 0. Now for the given value of Cp, T2, Ti, W will be minimum when T2 dash is a minimum. So this basically says that it is only possible when the T2 into T2 dash upon Ti square, this term is equal to 1. Because when this term will be 1, natural log of this will be equal to 0. So this gives us that T2 dash is equal to Ti square upon T2. So minimum work will be equal to Cp into Ti square upon T2 plus T2 minus 2Ti. A room is maintained at 27 degrees Celsius while the surroundings are at 2 degrees Celsius. The temperature of the inner and the outer wall, which are having the thermal conductivity of 0.71 watt per meter per Kelvin, are measured to be 21 degrees Celsius and 6 degrees Celsius respectively. Heat flows steadily through the wall, having the cross section of 5 meter into 7 meter and the thickness of 0.32 meter. Determine the rate of heat transfer to the wall, the rate of entropy generation in the wall, the rate of total entropy generation with this heat transfer process. Now the rate of heat transfer as per the conduction is equal to K into A into delta T upon L. The delta T is the temperature difference between the inner and outer wall, K is the thermal conductivity, A is the cross-sectional area, and L is basically the thickness of the wall. So this by putting the values we get the rate of heat transfer to be 1164.84 watt. Now taking the wall as a system, the entropy balance in the rate form gives us the entropy change rate of the wall is equal to entropy change rate associated with the transfer of heat plus the entropy generation associated with the wall. Now as the heat is flowing steadily, so the left hand term becomes equal to 0. Now the entropy change rate associated with the heat transfer will be equal to 1164.84 upon 294 minus 1164.84 upon 279, as 294 and 279 Kelvin are the respectively the temperatures of outer and inner wall. So the rate of entropy generation in the wall comes out to be 0.213 watt per Kelvin. The entropy change of the wall is 0 during the process since the state and hence the entropy of the wall does not change anywhere in the wall. To determine the rate of total entropy generation during this heat transfer process, we extend the system to include the regions on the both sides of the wall. So the entropy, that is total entropy change rate, is equal to entropy change rate associated with the transfer plus entropy generation rate, that is basically the total terms. So left hand term is 0. The entropy transfer rate associated with the heat transfer will be 1164.84 upon 300 minus 1164.84 upon 275 plus entropy generation rate total. which comes out to be 0.353 watt per Kelvin. In a certain process, a vapor, while condensing at 420 degrees Celsius, transfers heat to water evaporating at 250 degrees Celsius. The resulting steam is used in power cycle which rejects heat at 35 degrees Celsius. What is the fraction of the available energy in the heat transferred from the process at 420 degrees Celsius that is lost due to irreversible heat transfer at 250 degrees Celsius? Now, ABCD would have been the power cycle if there was no temperature difference between the vapor condensing and the water evaporating, and the area under CD would have been the unavailable energy. But in the real case, EFGD is the power cycle when the vapor condenses at 420 degrees Celsius and the water evaporates at 250 degrees Celsius. The unavailable energy becomes the area under DG. Therefore, the increase in unavailable energy due to irreversible heat transfer is represented by the area under CG. Now, Q1, the amount of heat extracted from the source, will be same in both the cases. Case 1, when there is no temperature difference between the two substances, that is vapor condensing and the water evaporating. And the case 2, when there is temperature difference between the two substances, that is vapor condensing and water evaporating. Means vapor is condensing at 420 degrees Celsius and the water is evaporating at 250 degrees Celsius. So T1 delta S is the amount of heat transfer for the reversible heat transfer when there is no temperature difference between these two substances, and T1 dash delta S dash is the amount of heat transferred from the source when there is temperature difference between the two substances, that is vapor is condensing at 420 degrees Celsius and water is evaporating at 250 degrees Celsius. Now this gives us delta S dash upon delta S is equal to T1 upon T1 dash. Now the work done in the cycle ABCD means for the reversible heat transfer case, which is represented by W, so that is equal to T1 minus T0 into delta S. Now W dash, which is the work done in the cycle EFGD, that is for the case of irreversible heat transfer, that is equal to T1 dash minus T0 upon delta S dash. Now the fraction of energy that becomes unavailable due to irreversible heat transfer is equal to W minus W dash upon W. Now putting the value of W and W dash and substituting the value of delta S dash upon delta S in the terms of temperature, which we have shown on the slide on the top of the slide, and we get the values all in temperatures, if you can see on the bottom of the slide. Now putting the value of all temperatures, we get the value of fraction of energy that becomes unavailable due to irreversible heat transfer as 0.26. In a steam boiler, the hot gases from a fire transfer heat to water, which vaporizes at constant temperature. In certain cases, the gases are cooled from 1100 degrees Celsius to 550 degrees Celsius, while the water evaporates at 220 degrees Celsius. The specific heat of the gases is 1.005 kilojoule per kg per Kelvin, and the latent heat of water at 220 degrees Celsius is 1858.5 kilojoule per kg. All the heat transferred from the gases goes to water. How much does the total entropy of the combined system of gas and water increase as a result of the irreversible heat transfer? Obtain the result on the basis of 1 kilogram of water evaporated. If the temperature of the surroundings is 30 degrees Celsius, find the increase in unavailable energy due to irreversible heat transfer. Now we can see that gas is cooled from state 1 to state 2. The figure has been shown, which is showing basically the TS diagram. Now the gas which is cooled from state 1 to 2, the process is taking place at constant pressure, and also the working fluid, that is water, that is getting heated from 2 to 1. This process is also taking place at constant pressure. Now for reversible heat transfer, the working fluid in the heat engine would have been heated along 2 to 1, so that at any instant the temperature difference between gas and the working fluid is 0. Then 1B would have been the expansion of the working fluid down to the lowest possible temperature, T0, and the amount of heat rejection would have been given by the area ABCD. When water evaporates at 220 degrees Celsius, as the gas gets cooled from 1100 degrees Celsius to 550 degrees Celsius, the resulting power cycle has an unavailable energy represented by the area AEFD. The increase in unavailable energy due to irreversible heat transfer is thus given by the area BEFC, which is shown as the shaded area. Now the entropy increase of 1 kilogram of water will be equal to latent heat absorbed divided by the absolute temperature at which this latent heat transfer takes place. So this is equal to 1858.8 divided by 273 plus 220, as 220 degrees Celsius is the temperature of the water that is getting evaporated. So that comes out to be 3.77 kilojoule per kg per Kelvin. Now Q1 is the heat transferred from the gas, and it is also equal to the heat absorbed by water during evaporation. So that is equal to mg dot Cpg into temperature difference, which is 1100 minus 550. And since it is also equal to heat absorbed by the water during evaporation, that is latent heat, so it is also equal to 1 into 1858.5 kilojoule. So mg dot Cpg is equal to 3.38 kilojoule per degree Celsius. Now the entropy change of the gas can be obtained by integrating del Q upon T from the limit Tg1 to Tg2. Now Tg1 is equal to 1100 degrees Celsius and Tg2 is equal to 550 degrees Celsius. But remember, in the expression, whatsoever comes, you have to put the temperature in Kelvin. So mg dot Cpg dot is equal to 3.38. So that has been put over here into natural log of 823 upon 1373, which comes out to be minus 1.725 kilojoule per Kelvin. Now the total entropy is equal to entropy of water plus entropy of gas, which comes out to be 2.045 kilojoule per Kelvin. Now the increase in unavailable energy will be basically the lowest temperature of heat rejection into the entropy change. So that comes out to be 303 into 2.045, and that comes out to be 620 kilojoule. Calculate the energy available in 40 kg of water at 75 degrees Celsius with respect to the surroundings at 5 degrees Celsius. The pressure of water being 1 atmosphere. Now if the water is cooled at constant pressure of 1 atmosphere from 75 degrees Celsius to 5 degrees Celsius as shown in figure, the heat given up may be used as a source for a series of Carnot engines, each using the surrounding as a sink. It is assumed that amount of energy received by any engine is small relative to that in the source, and the temperature of the source does not change while heat is being exchanged with the engine. So let us consider that the source has fallen to a temperature T, at which level Carnot engine operates, which takes heat at temperature T and rejects at T0, which is equal to 278 Kelvin. If del S is the entropy change of water, work obtainable will be minus m into T minus T0 into del S, where del S is negative. Now del W is equal to minus 40 into T minus T naught, and del S can be written as Cp del T upon T. So this expression becomes minus 40 Cp into 1 minus T naught upon T into del T. So now the maximum work obtainable, or you can say the available energy, will be equal to minus limit summation of the expression 40 into Cp into 1 minus T naught upon T del T from the temperature 348 Kelvin to 278 Kelvin. Now what we do, since we are having here negative sign and the limit is from 348 Kelvin to 278 Kelvin, we change the limit and then negative sign will disappear as we have changed the limits. So it becomes the integration from 278 Kelvin to 348 Kelvin for the expression 40 into Cp into 1 minus T naught upon T dt. So after integrating, we get the value of maximum work obtainable or available energy as 1340 kilojoule. Now the heat supplied is equal to 40 into 4.2 into 348 minus 278, that is 11,760 kilojoule. So unavailable energy will be heat supplied minus available energy. So that is 10,420 kilojoule. Calculate the decrease in available energy when 25 kilogram of water at 95 degrees Celsius mixed with 35 kilogram of water at 35 degrees Celsius. The pressure being taken as constant and the temperature of the surroundings being 15 degrees Celsius. The specific heat of water at constant pressure, that is Cp, has to be taken as 4.2 kilojoule per kg per Kelvin. The available energy of a system of a mass m, specific heat Cp, and the temperature T is given by the expression mCp into integration of the expression 1 minus T naught upon T dt from the limit T naught to T. Now, first of all, we want to find out the available energy of 25 kilogram of water at 95 degrees Celsius. So we put the value of T naught as 15 degrees Celsius plus 273 as we want the temperature in Kelvin. Similarly, the temperature T will be 95 degrees Celsius plus 273. So by the expression shown as the first equation on the slide, we can find out the available energy of 25 kilogram of water at 95 degrees Celsius. So by putting the unknown values and the limits, we find out the available energy of 25 kilogram of water as 987.49 kilojoule. By using the same expression, we find out the available energy of 35 kilogram of water at 35 degrees Celsius as 97.59 kilojoule. Now the total available energy can be obtained by summation of the available energy of both the streams, that is of 25 kilogram and that is of 35 kilogram. So the total available energy will be 1085.08 kilojoule. Now after mixing, if T is the final temperature, then you can see that one of the water who is having the high energy value or a high heat value will transfer its heat value or energy value to the other amount of water which is at lower energy value or lower heat value till they reach the equilibrium. So 25 into 4.2 into 95 minus T, this is the amount of heat given by hot water, which is equal to 35 into 4.2 into T minus 35. This is the amount of heat that is taken by the cold water. Now, P has been obtained at 60 degrees Celsius. Now, the available energy of 60 kilogram of water at 60 degrees Celsius, that can also be obtained by using the similar expression which we have used in the earlier slides. And this available energy for 60 kilogram of water comes out to be 803.27 kilojoule. So the decrease in available energy due to mixing can be obtained by subtracting the total available energy after mixing from the total available energy before mixing, and we get the value as 281.81 kilojoule. 2 kilogram of air at 500 kilopascal 80 degrees Celsius expands adiabatically in a closed system until its volume is doubled and its temperature becomes equal to that of surroundings, which is at 100 kilopascal 5 degrees Celsius. For this process, determine the maximum work, the change in availability, and the irreversibility. For air, take the value of Cv as 0.718 kilojoule per kg per Kelvin, and U, that is internal energy, can be calculated with the help of formula Cv into T, where Cv is constant. Now the change of entropy of air between initial and final states can be found out by the expression S2 minus S1 is equal to m into Cv into ln of T2 upon T1 plus m into R into ln of V2 upon V1. Now the maximum work, which is equal to U1 minus U2 minus T0 into S1 minus S2, can be written as m into Cv into T1 minus T2 plus T0 into Cv into ln of T2 upon T1 plus R into ln of V2 upon V1. As we have put the or substituted the value of change of entropy from the expression shown as the first equation on the slide. Now, putting the values, we can determine the value of maximum work, or you can say available energy, and which comes out to be 122.72 kilojoule. Now the change in availability, which is equal to phi1 minus phi2, can be written as u1 minus u2 minus t0 into s1 minus s2 plus p0 into v1 minus v2. Now as u1 minus u2 minus t0 into s1 minus s2 is the available energy or the maximum work obtainable, and the value of which has been calculated as 122.72. So we have written the value over here, and the second term has been calculated by putting the value of the parameters. So the change in availability phi1 minus phi2 comes out to be 82.2 kilojoule. Now the irreversibility, which is the, basically the maximum useful work minus the actual work, will be calculated. Now from the first law we know that the actual work is equal to del q minus du. So actual work comes out to be u1 minus u2 as the process is adiabatic. Now the irreversibility, which is equal to u1 minus u2 into t0 into s1 minus s2 minus u1 plus u2 is equal to t0 into s2 minus s1, or you can say t0 into the total entropy change of the system. Now for the adiabatic process, the entropy change associated with the surroundings is equal to 0. Now the irreversibility, which is equal to t0 into mcv ln of t2 upon t1 plus mr ln of v2 upon v1, can be found out by putting the values of the parameters, and which comes out to be 15.2 kilojoule. Air expands through a turbine from 500 kilopascal 520 degrees Celsius to 100 kilopascal 300 degrees Celsius. During expansion, 10 kilojoule per kg of heat is lost to the surroundings, which is at 98 kilopascal and 20 degrees Celsius. Neglecting the kinetic energy and potential energy changes determined per kg of air, the decrease in availability, the maximum work, and the irreversibility. For air, take the value of Cp as 1.005 kilojoule per kg per Kelvin, and enthalpy has to be calculated by using Cp into T, where Cp is constant. Now the change of entropy of air in the expansion process, that is between inlet and exit of turbine. Se minus Si is equal to mCp ln of Te upon Ti minus Mr ln Pe upon Pi. Now here E subscript is for the exit and I subscript is for the inlet. So for unit mass of air, we have put the formula as shown on the slide, and the change in availability psi I minus psi E is equal to Bi minus Be. So that can be written as Hi minus T naught Si minus He minus T naught Se. Now psi I minus psi E, which is equal to Hi minus He minus T naught into Si minus Se, is expressed as Cp into Ti minus Te minus T naught into R ln of Pe upon Pi minus Cp ln of Te upon Ti. Now putting all the parameters value, we get the value of Si minus Se as 260.7 kilojoule per kg. So the maximum work or the change in availability, which is equal to psi I minus psi E, is equal to 260.7 kilojoule per kg. From steady flow of energy equation, which is the first law applicable for the steady flow processes, we get the value of actual work. So Q plus Hi is equal to W plus H2. Here all the other parameters or all the other terms like the change in kinetic energy and change in potential energy terms have been neglected. So the actual work done comes out to be 211.1 kilojoule per kg. Here heat transfer is -1 as it is the heat lost. Now the irreversibility, which is equal to maximum work obtainable minus actual work, comes out to be 49.6 kilojoule per kg. Water at 90 degrees Celsius flowing at the rate of 2 kg per second mixes adiabatically with another stream of water at 30 degrees Celsius flowing at the rate of 1 kg per second. Estimate the entropy generation rate and the rate of exergy loss due to mixing. Take T naught is equal to 300 Kelvin. Now equilibrium temperature after mixing is given by the expression T is equal to M1 T1 plus M2 T2 upon M1 plus M2. Now putting the value of masses and temperatures, we get the value of equilibrium temperature as 70 degrees Celsius. Now the entropy generation rate is equal to 2.4187 into ln of 343 upon 363 plus 1 into 4.187 into ln of 343 upon 300, which comes out to be 0.0447 kilowatt per Kelvin. Now the irreversibility or the rate of exergy loss is equal to 300 into 0.0447, which comes out to be 13.41 kilowatt. So this was all for this numerical session. Thank you.